Okay, so we are going to talk about logarithms, which you have not seen before. So this is a new concept, but they're actually really, really cool. So logarithms, you've probably seen like on your calculator, there's a log button that stands for logarithm, and that's what we're going to talk about here. So what the heck is a logarithm, and like where did logarithms come from? So the way I learned logarithms was that they were the inverses of exponentials, which is true, but that is not why we came up with logarithms. So this is actually the guy who came up with logarithms. His name's John Napier. But let's talk about this like brief history of calculators. So back in, I don't even know, 200 or 2000 BC, so before Christ, these were the first types of calculators, and they were basically just like pebbles, and you could only use them for counting. Okay. And we also had, this was called like a abacus or something, and it was basically just like a counting machine, could just do pretty easy calculations on it. So then in 1642, and that's like, what is that? I don't know, almost 4,000 years later, that's when they came up with a mechanical calculator. But this could do addition and subtraction, and then multiplication and division by repetition. But if you're doing multiplication and division by repetition, that still is taking a long time, right? There's another example of what that mechanical calculator looked like. And these are actually calculators that people use. Like, imagine this. And now we have calculators on our phones that we just carry in our pockets. Like, that's kind of crazy. So then fast forward. So now we've gone from 1642 to 1902. So we are fast forwarding like 100 and, or not 100. How long is that? 1642. Like 300 years almost, 250 years. So this was when the first mechanical or non-electronic calculator actually looked like. So this calculator could do a lot of stuff just like that other one where we'd add, subtract, multiply, and divide. Like the same one that Pascal made in the Renaissance that we were just talking about. Okay, so, and then we can fast forward a little bit further, and then we get into our first like calculator that we know of today, in like the I don't even know what it was, like 60s or something, like really not that long ago. And I might have just made that number up. But anyway, so this John Napier guy was like, okay, people are not studying mathematics because it's tedious and it's hard and we have to make all these calculations. And he wanted to make math more applicable, I guess, and he wanted to help advance the scientific community. So that's when this guy came up with what we now know as logarithms. Okay, he was kind of an interesting dude. His expertise ranged from like philosophy, religion and politics, even astronomy, military intervention, and agricultural improvement. So he was a very well-rounded, smart guy. But it's his mathematical work that he is mostly remembered for. Okay, and he quoted this: the difficulty and the difficulty and prolixity of calculation, a toil which is apt to deter most people from the study of mathematics. I have all my life, with what powers and little genius I possess, labored to eradicate. So he's trying to make math easier for people who don't want to do it because the calculations suck. That's basically what he's saying. So pretty cool. He was the first one who came out of it. And then this Jos Burgi guy, he was a clockmaker in Switzerland, was it? Yeah, clockmaker in Switzerland. And he kind of was thinking the same thing at the same time as John Napier. He was like, okay, like, why are we doing all these calculations? Like, we're not able to advance the way we want to. He was probably like, I don't know, wanted to make his inventions a little bit better. I don't even know. I don't know exactly what his motivation was, but he, at the same exact time, helped discover logarithms also. And fun fact about him, he so he actually, like, you could buy these watches now, these Bergy watches, and they look pretty fancy. Like, I would buy one, maybe. I don't know. But then these are some of the other things he has made. So he's kind of an interesting dude, but he is not given as much credit. And that's one thing about history. Like, I know I'm a math teacher, but one thing about history is you always have to look a little bit deeper than, like, what is in the textbooks or what is taught to you, because there's always some forgotten person in history. There's always some story that we do not know, and it's really important to try and get every side of the story. Anyways, that's my spiel on history. Okay, and then this Henry Briggs dude comes around way after they created these logarithms, and he wanted to make them a little bit better. So then he went and did his thing, made them a little bit better. Okay, and we don't have to read all this stuff. Basically, we changed logarithms. Logarithm helps advance math. Wow, that was really good. Logs helped advance. They changed multiplication into addition problems. And addition is way easier to do by hand than multiplication is. And so that was a huge, huge leap in mathematics. Okay, this video is going to be linked on Canvas. Please watch it. It's a really cool video. It goes over like how to use log tables. We have calculators now that do all of this for us. But if we were living like, I don't know, 100 years ago, not even 100 years ago, 30 years ago, we would have had to use these log tables. Okay, but let's go a little deeper into this. Okay, so there's two different log bases. So we have log base 10, which this is what we call the common log. And this was what Henry Briggs came up with. So these are the tables that Briggs came up with. So just remember the biggest thing right here, and I would write this down. I know you probably haven't written anything down yet. Write that down. Log base 10 of x equals log of x. Okay. And then the other one that we see a lot is log base e of x, which is, we write that. This is called the natural log of x. And this is what John Napier came up with. Okay, and it's actually really cool that he came up with this e. E is a number in math. So this is the number 2.71828, blah, 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 blah. It's a lot like pi. It pops up in a lot of places. So this is called Euler's number. It's not Euler, it's Euler. It's an irrational number. It's the base of logarithms, and it's found in a lot of interesting areas. So like calculating e, if you just do 1 plus 1 over n to the nth power, and the limit as that goes to infinity, you'll end up getting e, which is kind of cool. Another calculation, so 1 plus 0 factorial. Factorial, if you want to know more about factorial, I can talk to you about it. But that also gives us e, which is cool because that's like a weird thing that will give us this number. Here's a way to remember e. Don't really care about that, I guess. Its slope is always its value, which is cool. I know a lot, you're probably like, oh, this doesn't matter. It appears in finance, so like compound interest. I am recently investing in the stock market, and I have been just completely blown away with like compound interest and all this stuff. So that's super cool. And E pops up in finance everywhere, which is crazy. And then Euler's formula. So there's just a ton of applications for E. And if you are curious about them, I definitely would go look them up. It's pretty cool. Okay, anyways, so they are the inverses of exponentials. Logarithms are. And this wasn't discovered until like 200 years after logarithms were actually around, which is crazy because like when I learned logarithms, I was taught that they were invented because they're the inverses of exponentials, but that's not true. Logarithms were invented way before we even realized they were the inverse of exponentials. So that kind of blew my mind. I know I'm probably sound like such a math nerd right now, but whatever. So basically, this log base b of a equals c is the same exact thing as b to the c power equals a. because they're inverses of each other. These statements are equivalent statements. Okay, and this is where I would start writing stuff down. So we have this logarithmic form, so log base b of x equals y. And in the exponential form, that's the bases, so the base b to the y power equals x. So the biggest thing here is that your answer to a logarithm is the exponent to the exponential. Bases stay the same, and then this middle part is your answer. Okay, and we'll go through right now how to write these. So the biggest thing, if you can remember first, last, middle, you can change between any logarithm and any exponential. So if we look at this, log base 3 of 9 equals 2. If I just remember first, last, middle. So the first number that pops up is the 3. The last number is a 2, and the middle number is a 9. Which, that's a true statement. 3 squared does equal 9. Cool. If we want to change this one to an exponential, if we just remember first, last, middle, so that's 4 is the first one, negative 2 is the last, and the middle is 1/16. Sweet. Again, just remember first, last, middle, so this will be 9 to the 3/2 power equals 27. Okay, just remember first, last, middle. If we wanted to do the opposite, oh wait, not the opposite yet. We have these ones. So if you have log of x equals 3 and ln of 2 equals y, well, log of x, we can write that as log base, because this is the Henry Briggs dude. We can write that as log base 10 of x, because remember log of x, or log equals log base 10. And then that's going to be first, last, middle, 10 cubed equals x. For the ln of 2 equals y, well, this is going to be Napier, and that's going to be log base e of 2 equals y, because ln is the same as log base e, and then that's going to be e to the y power equals 2. Cool? So if we want to go from an exponential to a logarithm, we can still just think first, last, middle. So like this one, first, you always write the log, and then first, last, middle. So this would be the first, this is the last, first, last, and this is the middle. Okay, we can do the same thing here. So this would be log base 2, because the first, and then the last of 1/8 equals the middle term, which is negative 3. This last one will be log base 8, because first, last is 16 equals the middle. Cool? So that's log base 14, blah, blah, blah. We did these. Okay? These ones. So if we have 10 to the x equals 493, well, we can rewrite that as log base 10 of 493 equals x, which log base 10 is just the same as log. So log of 493 equals x. This one, log base e of 7 equals y, which log base e is ln, so that's ln of 7 equals y. Cool? Okay, last thing, we're going to evaluate these. And we're going to use our knowledge of exponentials to do these. So basically, if we have log base 7 of 49, well, that's the same as saying, let's just say this equals x, okay? We want to know, first let's change this to an exponential. So that's the same as 7 to what power equals 49? Or we could just rewrite this as 7 to the x power equals 49. Okay, so then what would x be? Well, x would be 2. Right? Because 7 squared equals 49. Right? Let's look at this one. So this is saying 3 to what power equals 27? Or we could write this as like, oh, yeah. So then we could do like 3 to the first power, well, that's 3. 3 to the second power is 9. 3 to the third power is 27. So log base 3 of 27 equals 3. Okay, this one, so we want to know 9 to what power equals 1 over 81. well, that's going to be, like 9 to the first power is 9. 9 to the second power is 81. But we want 1 over 81. So then we could go backwards. Well, 9 to the 0 is just 1. 9 to the negative 1 is 1/9. 9 to the negative 2 is 1 over 81. So this would be negative 2. This one, so log of 100, well, that's the same as log base 10 of 100. So that's saying 10 to what power equals 100, which would be 2. Here, this would say 12 to what power equals 1. Anything to the 0 power is always 1, so this is going to be 0. Okay, last thing we're going to do here. So we're going to evaluate some logs, but now, like, this isn't as easy to do. So we can use our calculator. And even for all of these ones, you could have just used your calculator, okay? So this one is saying, like, 8 to what power equals 32? Well, I'm not sure because 8 squared is 64, so it's got to be somewhere between 1 and 2, and I don't know how to figure out that number. So what we're going to do, I have no idea what I'm doing. We're just going to use the change of base here. So basically, in your calculator, you can click, there's a log button. It's right next to the 7 key. And we're just going to do log of 32 divided by log of 8. And make sure you close the parentheses after the 32. And you get 1.66666, which is about, or it is 5/3. Okay, we could do the same thing here. Or then 8 to the 5/3 power does equal 32. You can always double check yourself. So here, log of 54 divided by log of 2, you get 5.7549, which 2 to that power does equal about 54. This last one, log base 10 of 294. Well, log base 10 is the same thing as just log, so then you can just put log of 294 into your calculator. Okay, ln of 7, there is a button on your calculator. So then you just put in ln of 7, you get 1.9459, which e to that power is approximately 7. Cool? All right, bye guys.